Today we're going to discuss solutions to u dot equals AU where the eigenvalues of A are complex. So let's start with the example matrix A equals 1 minus 1, 1, 1, which is a relatively simple example. We'll talk through the solution, say something about the general method, and then attempt to do a problem that's a little more complicated. So in this particular case, since A is 1 minus 1, 1, 1, the determinant of A minus lambda I is 1 minus lambda minus 1, 1, 1 minus lambda, which produces 1 minus lambda squared plus 1. You multiply that out, you get lambda squared minus 2 lambda plus 1, or lambda squared minus 2 lambda plus 2. Quadratic formula tells us that lambda is 2 plus or minus the square root of 4 minus 8 over 2, which is 2 plus or minus 2i over 2, which is 1 plus or minus I. Okay, so we're going to do this the way that we attacked the problem when we had real eigenvalues. We're going to take lambda equals 1 plus I, plug into A minus lambda I times AB equals 0, 0, and solve for the eigenvector AB. So A minus lambda I turns out to be 1 minus lambda minus 1, 1 minus lambda. You plug in 1 plus I, and you end up with minus I minus 1, 1 minus I. So we take our matrix, and the first thing that we do is we switch row 1 and row 2 so that we can get a leading 1 up in the A11 position. Now what we can see is we need to multiply the top row by I and add it to the bottom row. And when we do that, we get a 0 here. I times minus I is 1. You add that to minus 1 and you get a 0. And our matrix is now in reduced row echelon form. We've got a 0 row and we've got a free column. And the free column is for the variable b. So b is t. This equation reads a minus ib equals 0. So a is ib, which is it. And our eigenvector is itt, which is equal to t times I1. So that means that U1 is the eigenvector I1 times e to the eigenvalue 1 plus I, t. And now we're going to use what we know about complex exponentials to write that as e to the t, which is the real part, times e to the it, which we know is cosine t plus I sine t, right? So that's the idea. This is e to the t times e to the it, and e to the it is cosine t plus I sine t. Now we're going to do the same thing with the other eigenvalue, 1 minus I. We plug in and discover that our matrix is I minus 1, 1, I this time. We switch row 1 and row 2 as we did before, and this time we multiply by I and subtract. Okay, I times I is minus 1 subtracted from minus 1 is 0, so we've got our 0 row again, and this thing is in reduced row echelon form. So we have a free column here. We read across b is t because that's for the free column. This equation is a plus ib is 0. That means that a is minus ib, which is minus it. Our eigenvector is then minus itt, which is t times minus I1. U2 is going to be the eigenvector times e to the eigenvalue, which is 1 minus it. And we write this thing out again. That's going to be e to the t times e to the minus it. And what's e to the minus it? It's the cosine of minus t, which is cosine t, and plus the sine of minus t, which is minus sine t. Now, look carefully. This should look sort of familiar, okay, as should this. The original problem where we had u1, our eigenvector was I1, and this was cosine t plus I sine t. These are conjugates. So let's remember what a conjugate is. If you've got a complex number, alpha plus beta I, the conjugate is defined to be alpha minus beta I. Properties we've seen before is the conjugate of a sum is the sum of the conjugates, and a conjugate of the product is the product of the conjugates. So U2 conjugate is the conjugate of our eigenvector times the conjugate of e to the t times the conjugate of cosine t minus I sine t, and the conjugate of our eigenvector, conjugate of minus I, is I. The conjugate of e to the t is e to the t because e to the t is a real number. And remember that the conjugate of a real number is just the real number. And now the cosine of t minus I sine t is the cosine of t plus I sine t, and that's u1, the vector we had previously. And that means that the conjugate of the u2 vector is u1, and conversely, the conjugate of u1 is u2. Now, why is this true? And it's true in general. And the theorem is if A is a real matrix, if V is an eigenvector with eigenvalue lambda, then V conjugate is going to be an eigenvector with eigenvalue lambda conjugate. Why? Because if you've got AV equals lambda V, an eigenvector, then if you conjugate both sides, they're going to be equal. So the conjugate of A times the conjugate of V is going to be lambda conjugate V conjugate. A is a real matrix. The conjugate of real numbers are real numbers, same real numbers. So we've got A conjugate equals A. And that means this equation becomes A times V conjugate is lambda conjugate V conjugate. And read what this says. It says V conjugate is an eigenvector with eigenvalue lambda conjugate. For the equation u1 dot equals AU1, we have that u1 is eigenvector times e to the eigenvalue t, and that's a solution. But then according to what we just did, so is u2, which is the conjugate of v, which is also an eigenvector, with eigenvalue lambda conjugate, and that is exactly u1 conjugate. So why do we care about this? Well, what it says is, if you can find a solution u1, which is eigenvector e to the eigenvalue t, you get that u2 is eigenvector conjugate e to the eigenvalue conjugate t as a solution for free. Okay, so if you know a u1 from this method, you get a u2 from this method for free. Now let's pop back to our problem. u1 was minus I1 e to the t cosine t plus I sine t. And when we multiply this thing out, what we're going to get is e to the t cosine t times minus I. And I sine t e to the t times minus I times minus I is 1. And that gives us this e to the t sine t term here. So the point here is that this product gives you the imaginary part, and this product gives you the real part. Now we do the same thing down here for 1. We get e to the t cosine t is the real part, and e to the t I sine t is the imaginary part. So we can write u2 down. Here's u1 that we just calculated. u2 is the conjugate, which you can see the only thing that's happened here is this minus has changed to a plus, and this plus has changed to a minus. Now, as previously, when you have complex solutions that are conjugates, you can add them and subtract them and get other solutions. So if you add u1 plus u2, what happens is the imaginary parts cancel, and when you divide by 2, you just get e to the t sine t, e to the t cosine t, because the sum of these two was give us the 2. You divide by 2, you just got that. And notice that this is exactly the real part of u1. Now we're going to play the same game, but this time we're going to subtract. And when we subtract u1 minus u2, what you're going to see here is that when we're subtracting, the real parts cancel, and we're going to have, subtracting u2, we're going to get another minus I, with this minus I, which is going to be 2 of them, okay, plus I, minus minus plus I, so there are 2 of these. When you divide by 2I, all that you're going to get is the imaginary part of u1, which is this. Okay, so what we've discovered here is that if you just looked at u1 and never bothered with u2, the real part of u1 gives you a real solution, and the imaginary part of u1, and remember the imaginary part is the real number that gets multiplied by I, the imaginary part of u1 gives you a second independent solution. So just looking at the eigenvalue lambda 1, we produce u1 and we produce 2 real solutions. This is a general result. For a complex eigenvalue lambda, we're going to get 2 solutions. The real part of the eigenvector times e to the eigenvalue t, and the imaginary part of the eigenvector times e to the eigenvalue t. So let's do a slightly more complicated example. Again, it's u dot equals AU, but this time A is the matrix 1 minus 4, 2 minus 3. We look at A minus lambda I, 1 minus lambda minus 4, 2 minus 3 minus lambda. We want to calculate the determinant to get the characteristic polynomial. This product minus that product ends up giving us 1 minus lambda times minus 3 minus lambda. Minus minus 8 is plus 8. And when you do the algebra here, you end up with lambda squared plus 2 lambda plus 5. Quadratic formula gives us minus 2 plus or minus the square root of 4 minus 20 over 2. That's going to be the square root of minus 16, which is 4i. You divide everything by 2 and you get minus 1 plus or minus 2i. So all we need to do here, based on what we've seen before, is worry about one of the eigenvalues, and we're going to look at minus 1 plus 2i. We take the eigenvalue lambda, we put it into this matrix, and we end up with 2 minus 2i here. We end up with minus 2 minus 2i here. And this is the matrix we're now going to row reduce to find the eigenvector. Now we row reduce the matrix. The first thing that we do is switch row 1 and row 2 so that we can get a 2 up here. Then we divide the top row by 2 so that we have a 1 in the 1, 1 position. And now we want to clear this column, so we need to multiply this row by 2 minus 2i and subtract it from the bottom row. and we end up with obviously a 0 here, but we also get a 0 there, and that is because 2 minus 2i times minus 1 minus I is 2, plus 2i minus 2i minus 2, which is minus 4. So minus 4 is 0. And that leaves us with a matrix in reduced row echelon form. You can see that the B column is free, which means B is T, a free parameter. A minus 1 plus I, B is 0. And when you put this on the right-hand side and realize that B is equal to T, you get that A is 1 plus IT. And we end up now with our eigenvector 1 plus IT, T. And when you factor the T out, you get 1 plus I, 1. And we'll take our eigenvector to be 1 plus I, 1 by setting T equal to 1. And according to what we know, that means our solution is the eigenvector 1 plus I, 1 times e to the eigenvalue, which was minus 1 plus 2i, t. Now what we do is we take the exponent, which was the eigenvalue, and break it into the real and imaginary parts, and we end up with e to the minus t times e to the I times 2t. And of course, e to the I times 2t is cosine 2t plus I sine 2t. And now we're going to multiply that piece into the eigenvector and collect it into real and imaginary parts. And the real part, you got a cosine 2t. You've got I sine 2t times I, which gives you a minus sine 2t. The imaginary part, we've got a cosine 2t times the I. We've got an I sine 2t times the 1, giving us those terms. And then cosine 2t times 1 is real part down here, and I sine 2t times 1 is the imaginary part. And now our real solutions are just going to be the real part. Notice that it's still multiplied by e to the minus t. So we get a cosine 2t minus a sine 2t, cosine 2t times e to the minus t. And the other solution is the imaginary part, which is cosine 2t plus sine 2t, sine 2t times e to the minus t. And those are our two independent real solutions.